Thank you for joining the why and how of Cobot safety training. Cobot safety testing. The presentation will begin precisely at 2 o'clock. Thank you. Safety testing will begin in about 1 minute.
We have a lot to talk about and a short time to do it. My name is Bill Edwards, and I'm the Senior Manager of Technology Advancement and Collaborative Robotics here at Yasukawa America. We're going to talk briefly today about verification and validation as it relates to robots capable of operating collaboratively using power and force limiting. So the goal for this presentation is for you to walk away with 1, a clear understanding of what verification and validation means, 2, why it's required, 3, what's involved, and 4, where do I find the information and how to do it. So before we work our way through the presentation, I want to note that ISO 10218 and ANSI RAA 1506 are the safety requirements for industrial robots. And part 2 of those specifications deals specifically with robot systems and integration. And in 2012, ANSI adopted ISO 10218 parts 1 and 2. So really they're the same document, and you're going to see that throughout the presentation. So let's hop in and discuss the definition of what is verification and validation. So from ISO 10218 part 2 and ANSI RAA 1506 2012 part 2, verification is confirmation by examination and provision of objective evidence that the requirements have been fulfilled. And validation, similarly actually, is confirmation by examination provision of objective evidence that the particular requirements for a specific intended use are fulfilled. Well, to me, that's clear as mud. I get those two easily confused because the definitions are so close to being the exact same thing. So the way I want to think about it and the way that I want to present to you guys on how to think about it is translation from safety speak to plain English. So when we're talking about verification, what we're really asking the question is, did we build the thing right? And in this case, the thing is the safety system. And validation is asking the question, did we build the right thing? In this case, the safety system. So another way to help remember these two and keep them separate is verification comes before validation. So verification is performed during the design stage and is an engineer's analytical or mathematical effort to confirm that the safety circuit will achieve the risk assessment's required performance level. Validation is basically ensuring that the required safety function that you identified is reliably achieved in the machine's safety system. So are we required to do verification and validation? In short, yes. From ISO 10218, part 2 again, Section 6.1, you'll see that the robot manufacturer or systems integrator shall provide for verification and validation of design and construction of robot systems, including appropriate safeguarding devices. So I want to give you another translation here. In standard speak, if you ever come across the word shall, that means it's a hard requirement, and should is a highly suggested act. So you can see here that there isn't any wiggle room in what you're required to do. And remember, by the definition we found in 10218, we're required to provide confirmation by examination and provision of objective evidence. So I know what you're thinking. What does the collaborative robot safety specification, since we're talking about PFL, which is TS 15066, say about verification and validation? And you can see that it basically points right back at the parent standard. So what things might be involved in verification? Well, I think the safety analysis or the task-based risk assessment that we're required to complete would be there. Simulations, calculations, such as stopping distance calculations. Some other things involved in validation would be user tests under real-life conditions, such as force limit testing, speed limit testing, testing the robot's restricted space, access post restrictions using functional safety, or testing safety sensing devices. So let's get into the weeds for a minute and touch briefly on TS 15066, PFL, and risk assessments, and how all of that relates to verification and validation because it's important. So it's the thought process behind what's involved in all of this. So the goal of TS 15066 was to provide the industry with guidance specifically tailored toward the safety of collaborative robot applications. We're only going to be talking about one of the 4 modes of collaboration identified in the technical specification, and that's going to be PFL, because that's what we're framing in today. So here are the 2 very important concepts. The first concept is the concept of transient contact. So transient contact is between an operator and the robot system, where the operator, the body part, is not clamped and can recoil from the impact or from the contact. And the duration is less than or equal to half a second. Now you'll see the little graph on the right-hand side, and note that the peak force and pressure must remain in acceptable limits from the start of the contact and abate after half a second. And for this limit value, we use 2 times the quasi-static limit. And I know that's great, because what's quasi-static mean? Well, quasi-static is contact between the operator and a part of the robot system. And it should be noted here that the robot system isn't just the robot. It's the gripper, it's the tool, it's the part, and the robot itself, and any other part of the robot system, such as fixtures. So in this case, it's contact between the operator and a part of the robot system, where the body part can be clamped. Means it's pinched or stuck between part of the robot system and a fixed or moving part of the robot system. Think of a fixture. So, and also note for quasi-static that the force and pressure measurements must remain at or below the acceptable limits for half a second and then the entire duration. So another important concept in TS 15066 is pain is the precursor to injury. Now, why that's important is this. It forms the basis for using PFL as an acceptable safety solution in a risk assessment, because understand, we're doing all of this to try to reduce and mitigate any possible injury. So we had to establish in the specification a way to identify pain limits in order to know how to safely configure the robot. This information was provided by testing performed by the University of Mainz. So an important note here is that all resultant values were based on 1 centimeter square surface area. So a question that I'd like to throw out there, and we'll talk about it later in the presentation, is what happens if your surface area is less or more? And we'll get to that. Okay, another important concept in PFL was the whole safety concept, or the concept of using power and force limiting as a safety mitigation solution. So you can see by the slide, it says the robot system shall be designed, and remember we said shall is a hard requirement, shall be designed to adequately reduce risk to an operator by not exceeding the acceptable threshold values for quasi-static and transient contacts, as defined by the risk assessment in TS 15066. And then further, it goes on to say basically that the relevant contact events of the exposed body region shall be analyzed for the most stringent limits. So here again, we see the requirements for verification and validation, and now we're starting to talk about risk assessments. So we understand so far what verification and validation means and that we're required to perform it. The 2 contact scenarios involved with power and force limiting, and that we have to stay within certain limits, and that if we do, we know that injury is likely not to occur. Here's where TS 15066 knits all of that nicely together and frames it within the context of the risk assessment. So it also gives us guidance on how to calculate the theoretical maximum speed with respect to contact surface area and mass. And I'd like to point out that I say theoretical limits during validation testing or verification. So it doesn't take into account robot pose, and that means a lot with regard to how much force is actually going to be applied. And also these are theoretical maximums. The chart may say you could go 1900 millimeters per second, when in effect, very few robot manufacturers can even come close to achieving that. These are mathematical calculations found in this specification. So it's more just guidance. Okay. What I want to show by this slide and what I want to indicate is you can see by the calculations found in the TS that your allowable speed dramatically changes with surface area. So we did all of our initial testing with 1 centimeter square, but if I drop down to 1 millimeter square, say to the diameter of a 0.045 wire, you'll notice that the robot now was moving very quickly, or had the ability to move very quickly by the calculations, and now I'm barely moving or not moving at all. So we've also found that robot posture, again, has a profound impact on applied forces. So talking again about verification and validation, we know we're to provide objective evidence about whether or not what we've done is applicable. So what things should I be considering in an application? You know, we've talked about the need to provide this objective evidence. We can see here that we need to evaluate the contact events, including reasonably foreseeable misuse. So that's between the robot, because we're talking about robot systems. So it's between the robot and the operator, and that's all potential body areas that we can foresee, reasonably foresee, where the robot might contact the operator. We also have to take into account the end of arm tool. Where is it going to contact the operator? And how is it going to contact the operator? And also the part being handled. So if the part can strike the operator, what's involved in that? And are these events quasi-static or transient? Okay, so some more things to consider here. We need to evaluate the contact events with respect to the pain force limits. And those limits are found in TS 15066. But what are the surface areas involved in the contact? You can see that some of these contact areas, the surface areas, are quite large. Others are quite small. And remember what I said, we have to stay, during a contact situation, we have to stay within those pain force threshold limits. So the smaller the surface area, the sharper the edge, the more force is applied, more pressure is applied, and the robot can easily exceed those pain force limits. So when we're evaluating it, I threw on some examples here. You know, you can see the plastic lid down there. There's a lot of surface area. Those edges are rounded. There's not a lot of sharp edges, so chances are we'll be able to do that. That would be a good PFL application. I've had questions about handling. So for instance, die cast extraction. Notice that has very sharp edges on the flashing on the die cast part. Others don't. If I were handling that part, that would be something I'd very much have to consider, being at whether or not this is a valid PFL application. And another thing to consider that a lot of people don't, because they assume, because it's a power and force limited robot, that the robot, everything is safe. Well, let's say my tooling is safe and my part is safe, but I've got locating pins on my fixtures or sharp edges on clamps, and I'm evaluating whether or not if an operator's hand is in the way, and I'm looking at this as a quasi-static clamping situation. If I have a sharp fixturing pin, it's the same as having a sharp object on the end of the robot. So that's kind of why I threw on a conventional, not a safety-rated screw gun, but I threw on a conventional screwdriver, powered screwdriver. You can see that that has a very sharp edge, so we would easily exceed the pain force threshold limits in a quasi-static contact situation. Okay, additional items to consider when you're thinking about all the contact scenarios, and all of this has to end up in a risk assessment. Robot characteristics, speed, load, force, power, end effector hazards, layout with regard to separation distance between the robot and the operator, columns in the area, pinch points, operator location with respect to the robot arm, where's the operator normally going to be working, fixture design and related hazards, design and location and manual control of the guiding device. So if I can do lead-through teaching, is that in a good place that kind of keeps me away from where the hazard may be? Application-specific hazards, hot glue guns, welding. Some others might be handling sharp parts. So limitations caused by operator PPE, believe it or not, that's actually a thing too. If I have big gloves on, is that getting in the way of me accurately handling the robot? Environmental conditions such as chemicals, RF, or radiation, and the performance criteria of the associated safety functions. I do want to note that TS 15066, this is a shell. Objects with sharp, pointed, shearing, or cutting edges, such as needles, shears, knives, and parts which could cause injury, shall not be present in the contact area. So just for fun, I kind of threw that up there. Hint that robot carrying a sword would not be a good PFL application. So risk assessments involving PFL solutions. So since we're just discussing a very small part of an overall risk assessment, the two main areas we'll focus on just for conversational point are the two possible contact scenarios. And we're going to be talking about it framed just with respect to verification and validation. So one, in a risk assessment and a task-based risk assessment, we're going to evaluate and define the hazard. Then we're going to evaluate the risk level without safety solutions in place. So you can see that we have the task and that we have the hazard category and that we have the two different hazards. Then we have the failure modes, and then the severity class and the probability and the risk level. So you'll see that my severity, if I did nothing with a standard industrial arm, if I did nothing, or had a PFL arm that wasn't operating set correctly with power and force limiting, that my probability of avoidance is very low and my risk level is very high because the severity of injury is very high. So the next thing we do to reduce the risk is we look at applying safety mitigation solutions. In this case, I would apply power and force limiting and functional safety. I'm going to limit the speed and I'm going to limit my forces that the robot can apply. My severity, depending on, again, for conversational purposes, would drop down to minor severity because I am now not going to injure the operator. My probability of avoidance because of speed is very high, very likely, and my risk level becomes very low. So a point here is the risk level is low if the following: if the contacts identified in the risk assessment have been validated to be at or below the permissible force levels as stated in ISO 10-218-1506 and the 606. So notice I said if. I have to validate because I know that my surface area, my speeds, my forces, all of this stuff had to be set. And also, my surface area can vary. So I have to validate that. And it also varies with robot posture. So this is why we do verification and validation. Remember the objective is to provide confirmation by examination and provision of objective evidence. So we have to show evidence that our risk assessment said we had to mitigate the solution. We implemented the solution, and then here's my test results that proved I did what I said I was going to do to keep the operator safe. So you can see from start to finish, this is why we do verification and validation and why it's required. So this is a lot. So is there guidance for this? Yes. 2 years ago, we released the RAA-TR 15.806. And this document will help you answer the how-to question. So again, an important concept found in this document, a robot with PFL functionality is not to be considered safe out of the box, as the PFL robot is just a component in the overall collaborative application. So what's contained in this particular safety specification? How to use pressure and force measurement device, and to test the design limits in PFL applications. It comes with guidance for how to set up and test transient and quasi-static contact scenarios, measurement procedures, and measurement analysis. So we explored the why, explained the need, here's the how. Okay, what standards should I be using? Well, there's a lot of standards. And again, a lot of the new ANSI RAA standards track with what's going on in ISO, the ISO world. So if I were going to talk about risk assessments and I wanted to know how to do a risk assessment, I could look in ISO 12100, but in the ANSI world, a better document might be RAA-TR 306 and also ANSI B11.0 and B11.19. Those are three excellent specifications. Also, documents that you definitely want to have if you're considering power enforced application is RAA-TR 15.606 2016. That is actually ISO TS 15066. Same document. The other one I would consider was the one we just talked about and mentioned, which is RAA-TR 806 2018, which is the test methods for collaborative and power and force limited applications. Others you may want to consider, if you have the 2012 version of the 15.06, then you have ISO 218 parts 1 and parts 2. If you have, again, the 606, then you've got TS 15066. 13849-1 and 2, if I'm evaluating the parts of my control system to see if I achieve the required performance level, these are the documents that you want to look at for that. So I understand that that's a lot, and we had a very short time to talk about these things. I know everybody probably has some questions, and as Greg said, we'll be covering these at the end of the PowerPoint presentations. So with that, thank you so much for your time, and I appreciate your attention. And I'll turn it over now to the folks at InMotion.
So, short introduction of myself. I am Stefan. I am the Director of Sales at GTE, and I will keep it short and simple. And yeah, I appreciate to tell you a bit more about the how of Cobot safety testing today. I will start with the measuring system according to the R15806. To be more specific, the biofidelic measuring system and what that really means. And after that, we go over to the CoboSafe system. And yeah, I think the most important and informative part for you, the measurement procedure. So yeah, with a force and pressure measurement system, we try to simulate the human body, respectively the human body compression behavior, as realistic as possible. So you can imagine the measuring system like a crash test dummy. That's in generally what we are doing. Yeah, so what do we need for Cobot safety testing? So first, we of course need a measuring device, which consists of a force sensor, then a spring according to the ISO/TS 15066 or R15806. Then we need a damping element, and that one is a deviation from the ISO/TS 15066. Damping elements are just mentioned in R15806, and they lead to more realistic results. Furthermore, you have to apply a pressure sensor on top of the damping element. And last but not least, a microfiber cloth is applied. The R15806 mentions an additional layer of a Teflon film to minimize friction between moving plate and force gauge and damping element. That could be a problem when the force gauge is not exactly perpendicular to the path of the robot system, but from my practical experience, it's not really needed. So in a nutshell, one can say that the combination of damping element and spring is our biofidelic configuration, respectively simulation of the human body compression behavior. And for you to make things easier, you can imagine the spring and the damping element as a simulation of your bones and human fat or muscle tissue, the pressure sensor as a simulation of your nerves, and the microfiber cloth as a simulation of your skin. So for the correct measurement setup for each body region, you can simply look at table 1 of our 15806. For example, if you might have a possible contact at your hands and fingers, you have to use a damping element with shore hardness 70 and a spring with 75 newtons per millimeter. So let's have a look at the influence of different spring constants. So the table on this previous slide, there are mentioned 9 different spring constants. So what is the influence of different spring constants? Let me give you a short insight of that topic, of that spring topic. If just safety is your goal, it is sufficient within the intended use and foreseeable misuse to use only the worst case scenario. So that means a hard spring like the 75 Newton per millimeter for body regions below the head. If it should be necessary within the scope of foreseeable misuse to assess a contact in the area of the forehead, a spring of 150 Newtons per millimeter has to be used. So I will give you a short example. And in that example, we would like to measure a clamping scenario at the abdomen. And therefore, we need a 10 Newton per millimeter spring, and we have to stay below 110 Newtons. And since the measurement is all about the stopping distance of the robot, we assume in this example the stopping distance of 2 millimeter after collision. So the robot stopping distance of 2 millimeter also compresses the spring by 2 millimeters. And that leads to a measuring value of 20 Newtons. And now let's use the harder one, the 75 Newton per millimeter spring. So with that one and stopping distance of 2 millimeter, we will receive a measuring value of 150 Newtons. So, and as you can see, with the 75 Newton per millimeter spring, we exceed our threshold. The result is that we, for example, do have to decrease the speed of our robot, that we do have to decrease our force limits. And with the respective 10 Newton per millimeter spring, we could increase the speed of our robot. So, of course, I know that is just a very theoretical example. The actual difference in the measurement results depends on robot type, sensor technology, or movement, for example. So, in a nutshell, if you want to get the best out of your application, it is recommended to use the respective spring according to the affected body region. If just safety is your goal, then you can use a harder spring as a worst case consideration, as long as you stay below the threshold. Let us now come to the influence of the damping elements. In this example, you can see the pressure distribution of a measured cylinder. It was measured without a damping element. And the pressure is concentrated at the edges with a maximum of 230 Newton per square centimeter. So when we use a damping element, you can see that the pressure decreases to only 73 Newton per square centimeter. So I would like to emphasize that these results are not falsified by using a damping element. And yes, as already mentioned on one of my first slides, you will get more realistic results. And like I said, these damping elements, they are just mentioned in R15806, not in the ICTS 15066. So yeah, microfiber cloth. Why do we need that high-tech microfiber cloth? We performed measurements with a cube and a 0.5 millimeter protruding grub screw, and with a 4 millimeter protruding grub screw, with and without microfiber cloth for each measurement. And as you can see here, the measurement without microfiber cloth, we received that deep red discoloration or pressure distribution. And with microfiber cloth, it was not measurable. So with a 4 millimeter protruding grub screw, we received similar results, similar pressure distributions. The 0.5 millimeter protruding screw is not noticeable by the human skin. However, the 4 millimeter protruding screw is. It's like a needle prick. So one can say that the microfiber cloth is a mechanical filter to filter out roughness on surfaces that the human skin cannot feel. So that's why we're using a microfiber cloth. So there was just a very short theoretical overview. I would now like to give you a short insight how CoboSafe can support you in measuring power and force limited applications. So of course, the CoboSafe system is able to determine force and pressure according to the currently most important standards like the 15066 or 15806. And like I mentioned on my first slides, CoboSafe is able to simulate the human body compression behavior as realistic as possible. So just a few key features of CoboSafe. That system is, I would say, self-explanatory. It has only one button to operate. The software guides you through to the finished project. For example, the R15806 mentions to record the test conditions like temperature and humidity, and that system is able to assist you here with an integrated thermal hygrometer. Often you will have a application, and maybe you will not have enough space for a large measuring system inside of the application. So CoboSafe supports here with very small dimensions to be highly practical. And if you of course have cycle time critical applications, then CoboSafe can help you here to optimize your speed. For selection of the required force gauges, so if we for the selection of the required force gauges, it is advisable to carry out the risk assessment first, and based on that, you know the affected body region, and you can easily choose the appropriate force gauge. But like I said, if just safety is your goal, then it's like worst case consideration, and you're good to go with the 75 Newton per millimeter spring. If you want to get the best out of your application, then it's recommended to use the appropriate force gauge according to the affected body region. So then you have to select the appropriate measurement pressure measurement system. Again, if your goal is safety and you do not have a cycle time critical application, the CoboSafe scan pressure measurement is recommended. It only determines the maximum pressure, that means the transient value, and is also a worst case consideration. These foils are consumables and cannot be reused, but I have to say that most integrators in the field, they're using that system with these pressure sensitive foils. If you want to optimize your application, then I would say the more sophisticated system, CoboSafe Tech, is recommended. And with that one, you can distinguish between transient and quasi-static pressures. For this purpose, the pressure is recorded over the measurement period in form of a video. So measurement procedure. Let's now have a closer look to the data collection with both systems, and how to execute a measurement. So with the CoboSafe scan system, of course you need a force gauge, you need these pressure sensitive foils and a scanner. So and first you have to determine the measurement points. So if you have done your risk assessment, if you have finished your risk assessment, you have finished the most complicated part when it comes to measuring an HRC application. That is one of the good news. So the measurement procedure itself is pretty easy. Once you find out your collision points, then you have to configure or set up your device to the or for the affected body region. You can have a closer look later on slide 13, table 1 from the R15806. Then you have to locate and secure the device inside of your application. And yeah, after that, or one most important point is that when you measure or you want to measure, then you have to ensure that only safety functions are enabled. So the measuring system is a single axis force gauge, and you have to ensure that the measuring plate of the force gauge is or it shall be positioned centered and perpendicular to the path of the robot system. So then you perform your measurement, and after the collision, you will receive transient and quasi-static forces from the force gauge, and the collision causes the Fujifilm to discolor red. So number of tests. For example, if your goal is only safety, and your measurement results are, for example, 50% below your threshold, yeah, then you will not exceed your threshold in subsequent measurements. If you want to optimize your application, so that means getting as close as possible to your to the threshold, yeah, test sample size most commonly used is a minimum of 3 tests with not more than a 10% variance at each identified contact. So data transfer to software is done in 2 ways. To transfer the force values, you have to connect the device to the PC either via USB cable or via Bluetooth in order to be able to evaluate the pressure film. You have to place it on the scanner, and the software then determines the pressure distribution and determines the maximum pressure. So when all measurements are completed, you just have to create a final measurement report. And I now have a short video for you that demonstrates the measurement process. And yeah, please just imagine that I am the robot.
Demonstrate today how to operate the device and how to evaluate the corresponding measuring results. This device can be operated easily and intuitively with only one button. You press the button to switch on the device and hold it down for a few seconds to get into the menu. Through further short pushes, you click through the menu. Keeping the button pressed for a longer time opens a menu item. For measuring force and pressure, we need the spring constant with a built-in color sensor, the damping element, and the Fuji Prescale measurement films. Start the process with selecting the right combination of spring constant and damping element, apply the damping element, put the measurement films on top, and make sure that the rough sides lie on top of each other. Finally, the microfiber cloth is applied. Now execute the measurement. The measured forces can directly be read in the display. The corresponding pressure is captured through the measurement film. The film turns red due to the pressure. The stronger the red discoloration, the higher the pressure. To evaluate the measurement, turn to our CoboSafe software. First, create a project and follow the instructions in the wizard. Enter all information needed. Select the used measurement equipment, set up collision scenarios, indicate robots used, define movement and collision points. Also select body regions by clicking on the body model. Now import the force data by selecting the measurement system using Bluetooth or USB connector. Open the measurement data, add further information and create your report. To import the pressure data, click Scan and select the appropriate scanner. For the scan, a calibration sheet is necessary. Put the measurement film on the scanner, rough side down. The calibration element is placed over the Fujifilm. Now perform the scan. In the software, select the area you want to evaluate. Check all parameters, add pictures and create a report. Create your combined force pressure result by connecting the two measurements by drag and drop. After all measurements have been assigned, the evaluation is based on the measurement results. These can be set pass or fail. In this example, the quasi-static area limit is exceeded. Finally, a log is created by opening the project window and clicking the corresponding button, and a report is automatically created in Word.
It's pretty easy to perform a measurement with that system. And again, if you have done your risk assessment, when you have found out your possible collision points, then you are finished with the hardest part of the PFL or Cobot's safety testing part. So I will now give you a short insight of our CoboSafe tech system. You need a sensor. It's an electronical film which needs to be connected to a handle. The handle is connected to a hub, and that one is connected to the PC. So it's quite the same like the measurement procedure I've presented before. You just have to place the measuring system at the point where you expect a collision between robot and worker according to your risk assessment. And after the collision, also here you will receive transient and quasi-static data for force and pressure. But in contrast to the CoboSafe scan procedure, with CoboSafe Tech you get two measurement curves as a result. One force measurement curve, the dark blue one here, and one pressure measurement curve, that is the light blue one. And with your mouse cursor, you can view the pressure distribution at any time during the measurement. So you can have a closer look here at the pictures on the right side. So again, I have also a short video for the measurement procedure with the CoboSafe Tech system.
For measurements with CoboSafe CBSF, the pressure measurements films of type 5051 and 5027 are used. The Versatech hub is used to convert the communication protocol of the Versatech handle to USB. The Versatech handle captures the data of the pressure sensor and transmits it to the Versatech hub. To put the device into operation, we open the lever of the handle,
we align and insert the pressure sensor into the opening slot slowly and controlled. We close the lever and we check for the green sensor OK light. Then we start the menu CoboSafe Tech from the menu bar and we select our test specification and respective measuring equipment. We set the parameters and select the appropriate pressure measuring film. Then we perform the sensor test by stroking. The functionality is indicated by green bars. To finally perform the measurement, we configure the measurement setup according to the respective standard. Then we place the measuring surface of the pressure sensor on the compression element and we finally perform the measurement. The measurement has now been created. The force is displayed as blue measurement curve. The pressure is displayed as a green measurement curve. A film was recorded for the pressure distribution. The film can be played or jump to the respective maximum values. The electronic pressure measurement method distinguishes pressure values for transient and static range.
Yes, so that was pretty much all of my content. But the best information at the end. We do have a US partner located in Chicago. It's in motion, and if you might have further questions or if you would like to receive a quote or something else, feel free to reach out to Gerald. He will be happy to assist you with any question you might have. That brings me to the end of my presentation. Finally, it only remains for me to say thank you very much for your participation and attention. And if you have any questions, please do not hesitate to ask.
Well, we've got one.
We have a few questions on deck. If anybody wants to take one.
Yes, I would like to answer the first question. Have you done any testing with a Cobot welding torch? No, not really. So that is a very special application, and yes, so in that case, you have to ask yourself, is it really should it be a PFL application, or should we maybe cover it with a protective fence or something like that? So welding applications are a little bit special. So no, I've I've not done Cobot safety testing at a welding application.
Stefan, I will answer the training on the systems for customers. So we have web trainings available, since obviously we are all hiding at home, and with COVID, it worked out pretty well with the customers who purchased systems the last 1.5 years. We're doing some web trainings. You saw the video. Sometimes that video is also quite enough for the customers to get it going at first.
If and in motion, do you provide training on
Yes, we
these
do.
systems for customers?
Yes, we do.
Right. For assigning contact
We've got a
areas, is
little
the measurement
time. I
taken
can-
only at the highest perceived risk or at all risks? Anybody want to handle this?
Yeah, I can take that one. So what we have to provide objective
Well, if,
evidence based on the contact
If we didn't get to all
areas
the questions,
identified in our risk
we
assessment.
will be reviewing
So at this-
the chat log, and we can get back to any of the unanswered questions by email. And if there's any other coming in that we missed, you want to answer now, presenters?
I could try to answer Aaron's.
Yeah, go ahead.
Okay, so assigning contact areas is a measurement taken only at the highest perceived risk or all risk. So what we need to do is provide that objective evidence for our risk assessment. So if we identified several body areas that could be contacted, we're going to provide objective evidence that all of those risks and those forces can be mitigated. For instance, Yasukawa Robotics, we can change what force levels we're operating at any point in time. So if I could strike your chest, obviously there's a lot more force, there's a lot more energy that can be distributed by hitting your chest in a transient contact versus hitting your finger. So conceptually, I can move faster when I'm going to strike your finger in a transient contact than I could if I were going to hit a larger body part where there's more mass and thus more energy being transferred. So yeah, I would say that you have to take them at all of the perceived risk and body areas. You could go with the worst case, but that's not indicative of the application as a whole. And it also wouldn't be indicative of being struck by the robot without the part or being struck by the robot with the part. So hopefully I answered the question, because that's a larger topic.
I would like to add something to your answer, Bill. Here in Germany or in Europe, it's like that we most of the time we do consider realistic collision points. So that means that we do consider possible collision points where the worker has to interact with the robot. So we do not consider scenarios, for example, that the worker gives the robot a high five, or that the worker takes a snap inside of the application. So we do consider realistic collision scenarios. So are there any questions left? I have a little bit problems here with the chat or question function. It's loading, so I can't see any other question.
Okay. So if everybody can hear me okay, several questions have come in about interpreting TS 15066 state strikes that are not allowed at any speed. Strikes to the head, face, and neck are not allowed at any speed. That's actually not what TS 5066 says. Contact exposure to sensitive body regions, including the skull, forehead, larynx, ears, face, shall be prevented whenever reasonably practical. Notice it doesn't say can't and never. It says whenever reasonably practicable. Your goal is to reduce the forces to safe, acceptable limits. So what they're saying here is that they shall be prevented whenever they can be prevented, whenever it's reasonably practicable. It doesn't say never. I see a lot of people put these systems into place, and if there are concerns about strikes to the head, face, or neck, they try to first engineer the hazard out by moving the robot to a lower elevation where strikes to the head, face, or neck aren't reasonably foreseeable. And in the case of, say, palletizing, where the robot may be mounted on a bit of a riser, they'll put padding around the gripper, they'll put padding around the robot, they'll slow the robot down, and they may put extra ESPE, such as light curtains or scanners, to actually stop the robot before the person gets too close. So it depends on the application, it depends on the process requirements of the application, and it depends on what you can do to lower and mitigate the risk to make it reasonably practicable. But you'll note, though, that the standard doesn't say can't. It just says shall be, which again, I said the word shall is a requirement, shall be prevented whenever reasonably practicable, which means whenever you can reasonably prevent that contact scenario, you shall. Very simplistic answer to a question that we probably would take a lot longer than that to truly sort out, but it varies by application and it varies by people's definition of what's reasonably practicable.
If we didn't get to all the questions, we will be sharing those out with the presenters, who will get back to you personally by email. Again, we will be emailing copies of the slides as well as a link to the recording of this presentation. And I'd like to thank our presenters and thank our audience for attending today. I appreciate it.